Today we're going to talk about turbo machines. My group is made by Luis Becquer, Kayla Fernandez, Solange Lizama, and me, Alejandro Solano. The objective of this presentation is to explain how turbo machines work, how we can represent them with blades and velocity diagrams, the difference between a turbine and a pump, how to determine the operating point, the importance of minimizing loss in turbo machines, effect of size and speed on a family of turbo machines, and how to select an appropriate turbo machine for a particular application. Turbo machines are mechanical devices that consist of several blades attached to a rotor that extracts or adds energy from a fluid. These usually have a casing that forms an internal flow. Turbo machines can have three different types of flow, which are axial, mixed, or radial. This depends on the predominant flow direction relative to the rotor axis as it passes through the blades. Here we can see simplified examples of each flow. The first picture is an example of radial flow, where the fluid moves in the same direction of the blade, and the second picture, the fluid goes perpendicular to the rotor, making an axial flow. The velocity of the blade, which is labeled with a capital U, is denoted by the angular velocity of the rotor times the radius of one blade. We also have the absolute velocity fluid, which is denoted with a capital V, which can be seen as the velocity of the fluid seen from someone outside of the turbine, and by last the relative velocity, W, which is the velocity of the fluid relative to the blades. The absolute velocity is formed by the addition of the relative fluid velocity vector, and the blade speed. For this course purposes, it is always assumed that the fluid is perfectly guided by the blade. It is also assumed that the fluid enters and leaves the turbine at the same distance from the axis of rotation. These two assumptions are important to model the operation of turbo machines with velocity diagrams. To draw one of these, you have to look at the turbo machine from the top of the blade. Then you have to draw two triangles with the vector addition as seen in the image. W is always going to be parallel to the blade, and U will be the tangential component.
So I will be talking about the basic differences between a turbine and a pump. Within a turbine, the tangential component of the force on the fluid is opposite to the direction of the blade motion. It decreases the energy of the fluid and then converts the work from the fluid to the blade. Within a pump, the tangential component of the force on the fluid has to be in the direction of the blade motion. This adds energy to the fluid and does work on the fluid as well. And on the right is an illustration comparing the two different types of devices. So in order to classify between a turbine and a pump, we must look at velocity diagrams to determine the direction of the blade. So this illustration is taken from the book where they're trying to figure out what type of device is given in the problem. They're using the given inlet and outlet velocities as well as the angular velocity to determine the velocity diagram and what direction the blade is going in. So as you can tell from the velocity diagram and the other illustrations, this is in fact a pump. So in order to determine the operating point for when a specific pump is installed in a system, we must look at the intersection of the system curve and the pump performance curve. This point gives us the flow and head rate that satisfies both the system equation, which is the system curve, and the pump equation, which is the pump performance curve. And as you can see on the graph as well, there is an efficiency curve. And on that curve, there's also this point called the BEP, or the best efficiency point. So when we're looking at an operating point, we want to be close to the best efficiency point. So as you can tell, that is point A.
Centrifugal pumps are widely used because of their high efficiency, easy installation and maintenance, and also because their discharge is uniform and a continuous flow. I'm going to describe a performance analysis of a centrifugal pump and talk about losses and importance of minimizing them. The performance of centrifugal pump is described by a graph plotting the head generated by the pump over a range of flow rates at constant speed, like you can see in this graph over here. We have the theoretical head, which is also called Euler's head, and the equation that describes it's 1 over gravity times outlet tangential velocity times the real velocity. Now, the efficiency of a centrifugal pump depends upon hydraulic losses, this friction, mechanical losses, and leakage. The major contributor of losses in centrifugal pump are shock losses, which refer to the losses at the impeller caused by the mismatch of fluid and metal angles. We have the impeller friction losses, which can be found for energy dissipation due to the contact of the fluid with the solid boundaries, such as the diffuser. We have the volume friction losses, and we had these friction losses and recirculation losses. The actual pump head is calculated by subtracting from the theoretical head all the flow losses, like you can see in this equation over here, and the actual head is always going to be less than the theoretical head, and this is the graph that represents that. Now, the overall pump efficiency is the ratio of the power actually gained by the fluid to the shaft work supplied. We have, I have over here the equation for the efficiency, and then to calculate the shaft work, we use this equation. So it's going to be equal to the density times the flow rate times the blade speed times the tangential velocity. Now, minimizing losses on a centrifugal pump will minimize energy dissipation and will increase efficiency. At the best efficiency point, the pump operates most cost effectively, both in terms of energy efficiency and maintenance considerations.
In this section, I'm going to talk about the main aspects to consider when designing turbo machines. One of them is the effect of size and speed of turbo machines on operational parameters, and the other is the viscous effect of fluids. The fundamental pump design relies on the application of similarity laws to predict the effect of the change in size or on speed on the operational parameter of the pump, such as head rise, volumetric flows, and power. The similarity laws allow us to relate two different pumps of the same geometry but different operational rotor speed and impeller diameter. The fundamental of similarity laws are the dimensionless parameters called the head coefficient, the power coefficient, and efficiency. We can see that the head coefficient is related to the head of the system, the power coefficient is related to the shaft work put into the system, and the efficiency is given by the ratio between the work we get from the pump and the work that is put into the system. For very high random numbers, the viscous effects can be neglected, and these three equations are reduced as the following form. The expression inside the parentheses is the dimensionless parameters called the flow coefficient. The flow coefficient provides the similarity relationship among the family of geometrically similar pumps. Therefore, we can obtain relationships for the head coefficient, the power coefficient, and efficiency among pumps as well, which are given as follows. This expression relates the flow head power of pump 1 with a given rotating speed and impeller diameter to the same parameters of a pump 2 with different impeller size and speed. The idea of using the similarity laws is that from a non-operational head and volumetric flow of pump 1 with given size and rotor speed, we can determine the new operational parameters that a pump 2 with different size or speed will work at, maintaining the same efficiency. This is a pump manufacturer chart sample for a given rotor speed, which englobes the main parameters considered when designing pumps, such as the head, the flow rate, the impeller diameters, the power of the rotor, and the efficiency of the system of the pump. Another critical parameter to have in mind is the specific speed, which is given in the United States by this expression, which has a dependency on the head of the system. This implies that the specific speed will depend on the viscous effects of the fluid and therefore on the system Reynolds number. This dimensionless parameter will determine the type of pumps to be used in the system. These figures show the recommended type of pumps for a given range of a specific speed. Therefore, we can conclude that the type of pumps implemented will mainly depend on the viscosity of the fluid to be pumped.